The first speaker is Mingyuan Liu from Fudan University, and he'll be talking about diffing Android applications. Mingyuan.
Introduction. My name is Mingyuan Luo from Fudan University. Today I'm here to present ApkDiffer, a novel tool for accurate and scalable cross-version diffing analysis for Android applications. In a nutshell, ApkDiffer takes two different versions of the same application and precisely identifies methods which have been added, removed, modified, or remain unchanged. For example, method A here is aligned with A prime, which is modified, and method B has no alignment since it is removed, and method D is aligned with method D, which remains unchanged. Method alignment can ease the auditing of application updates, since it helps us focus on the exact change introduced by the application updates. And it also helps with the reverse engineering, since we can easily migrate the knowledge of the old version to the new one. In fact, method alignment is a graph matching problem. We can represent each application version as a call graph, where methods are nodes and calls are edges. The problem then becomes finding the correct correspondence of the graph nodes. However, this is where we run into our first challenge, the scalability. Graph matching is well known as an NP-hard problem, which means that its complexity explodes as the graph size increases. Additionally, modern Android applications are massive, containing tens of thousands of methods, which means that trying to match these large graphs is computationally infeasible. Our solution to this scalability problem is to divide the whole call graph into small subgraphs, which we call it functionality-driven graph composition. Here, we leverage the event-driven design of Android applications. In Android, a user clicks a button, the system sends a notification, or the component lifecycle state changes are all events. We treat the code that handles these events as distinct functionality units. And then ApkDiffer partitions the whole graph into smaller subgraphs, and each of the subgraph is corresponding to one of these functionality units. For example, we can separate all methods starting from the callback of the next button click to form a subgraph, which is marked as green in this figure. To identify the callbacks of these events, we manually construct a whitelist of framework classes where the callback interfaces are defined. And then we identify application callbacks that override these frame callbacks. Once we have these smaller subgraphs, we need to match them across versions. We do this by finding the unique event ID of each subgraph, which tends to be stable across versions. For example, the subgraph marked with green has a unique ID next button. And in the newer version, there is a subgraph which has the same unique ID next button. Then we can match them by matching this unique ID. Here is a concrete example that how we use the program analysis to locate the event ID. Briefly, we use data flow analysis to identify the GUI element of the onClick callback here. Now for our second challenge, accuracy. Existing work often make a trade-off. For example, linear assignment aligns the most similar nodes according to their code similarity, mainly uses node similarity but ignore the edge similarity. And another example is neighbor search. It sets up an initial set of aligned methods using simple heuristics such as containing the same string literals, and iteratively adds the neighbors of the aligned methods to this set. However, it focuses on the edge similarity but ignores the node similarity. Additionally, none of these existing works effectively handle end-to-end alignment, which occurs when the developer refactors the code. These figures show the cases of end-to-end alignment. Specifically, figure B shows a 1-to-2 alignment. In the old version, A calls method B twice and method C, but in the newer version, A calls method D and method C. However, D calls B twice, so they do the same thing as method A in the old version. They should be aligned. And figure D shows an example of end-to-end alignment. In the old version, method A and method D calls a sequence of methods, namely B, B, C, C here. And in the newer version, method A and method E calls the same sequence B, B, C, C. So A and D should be aligned with A and D here, since they do the same thing. And to our best knowledge, existing works literally ignore the end-to-end alignment. To tackle the accuracy, we introduce a three-stage process. The first stage is anchoring. We start by running a fast but basic alignment using linear assignment. This stage only considers the node similarity and possibly produces significant errors. And this stage can be formally modeled as an optimization problem. Specifically, given a matrix P where Pij equals to 1 means that method I aligns with method J. We search for all possible values of this matrix to find one that maximizes the sum of node similarities, which we denote the result as P star anchor. Second stage is refining. This is the crucial step. Here we introduce edge similarity to correct the anchoring result. The edge similarity here is defined as the percentage of correct aligned neighbors. This process can also be modeled as an optimization problem. We are still searching for an alignment matrix to maximize the sum of similarity. However, the difference here is that we use a new similarity matrix, SimFusion, which adds the edge similarity to its calculation. This figure shows an example. It notices that method B is matched with method C prime, but their neighbors don't match up well. The neighbors here are method A and method H in the old version, and A prime and D prime in the newer version. Here, method A is matched with A prime, which is correct. However, method H is not matched with D prime, which is unexpected. So the refining stage can confirm that B should not be aligned with C prime, and in consequence, it will search for a better fit like B prime. Finally, stage is expanding. In this stage, we are looking for those end-to-end cases. We do this by checking the neighbors of aligned methods to see if merging a smaller unaligned method back into its caller would create a much better match. For example, in this figure, we check the F prime, which is a colleague of the E prime. We merge F prime back into E prime as one single node, and then we use a new similarity matrix designed for two method sets to evaluate the similarity. And this helps us find a 1-to-2 alignment here. And here is the evaluation part. We evaluate the ApkDiffer against four baselines on our benchmark, namely greedy search, linear assignment, and neighbor search, and PE-joid. As the result shows, ApkDiffer significantly outperforms all others in both precision and recall. Specifically, it improves about 4% to 35% accuracy and 16% to 64% recall. In terms of the time cost, ApkDiffer spends about 24% of time on graph decomposition and about 57% on the method alignment. And in average, ApkDiffer needs 9 minutes to analyze one application. Although it is not the fastest tool, it has a reasonable time cost and the best accuracy. To prove its real-world utility, we use it to evaluate the evolution of privacy collection behaviors. Specifically, we evaluate 100 applications gathered from the Google Play Store, and the conclusion shows that many privacy collection behavior is added and many is deleted every quarter of the year. And we further investigate the causes of the privacy collection behavior, and we found that 70% are due to the functionality updates and some are due to the library integration. Most importantly, we can dive into the code. We found cases where updates introduce new privacy threats. For example, WeRecorder added the feature that slightly leaks the device ID to web pages. And another example is the Phone Master. In an update, it started tracking for GPS status and leaking location data from a shared component. And all of these cases are subtle but dangerous changes that tools like ApkDiffer are designed to uncover. And finally, ApkDiffer is fully open sourced. You can scan the QR code to get its artifacts, including source code and datasets. And if you have any questions on how to use it, please feel free to contact us through email. And thank you for listening.
Thank you for the excellent talk. Questions?
That's very nice. When you do the precision and recall, how do you know what the ground truth is?
The ground truth is since we can intercept the compilation process of each APK, and so in this process we can just mark the ground truth by some many worker and instrumentations.
When you do this matching of two different apps, so when you have two different versions, I believe most of the functions remain the same, isn't it?
Yes.
In such a case, if most of it is the same, if I take a very simple naive scheme that just says the function is exactly the same, they are matching, how much percentage would that be?
Oh, we actually we do not calculate the percentage of the functions that totally remains unchanged. We just evaluate the accuracy like precision and recall here.
Okay. The second question, you had a slide on expanding, right?
Yes.
So there, do you take into consideration that a functions may be called F1 first, then F2, or F2 followed by F1? Do you maintain dependencies? Do you have to take care of dependencies as well?
Dependency? You mean that in such as
yeah, let's say
this case?
Yeah, let's say calling B1 first B and then B2.
Yes.
And I change it to B2 followed by B1. Is it same or it's different?
You mean that if we change the sequence of this BBCC method? Or?
Right.
Yeah. We are this sequence sensitive. We can identify they cause the same sequence here.
Oh, you are sensitive to that?
Yeah.
Okay, cool. Thank you. Any other questions? No? Let's thank the speaker again.